Yes? Okay. Physical science time. Today we are talking about motion in a line. Can you think of a cuter name for motion in a line? Probably linear motion. Yep. So let's name it that. Linear motion. This is the second video in 1 week that I have done entitled Linear Motion. The last one I gave to 8th graders. You know them. This one's going to be different because why? You already know the answer. 9th graders, better, smarter. All those things are true, but the content is going to be different because... Who said it? Aiden? Ramrock. Yeah, and we're all 9th graders here. Yeah, all of us. All of us. Some people. Okay, some people. So this is motion in a line. You've seen things move in a line before. I started out the last time I did this video with a magic trick, but you guys are beyond that, so I'm going to do a little better magic trick. I'm trying to think of a way to make it actually better because you're adults, and so you need to have a good magic trick. Okay, check it out. Let's say, give me an example. I want an object. I want an object that you think I can't draw because I'm going to prove you wrong because I'm a great artist. Okay, let's do dinosaur because that's cooler. Yeah, it is going to look very. Look at that. She's got a little bit thick in the posterior department. But check it out. Okay, now look at the dinosaur. Let's give her a name. Okay, this is going to be a fun video. Let's give her a name. Linda. Linda is a cute name. I know some people who are dinosaurs. Okay. Now, okay, here's the magic trick part. Close your eyes. Close your eyes. And if you're watching the video, Kylie, I'm not joking. You need to close your eyes. Put your heads down like you're going to vote. Put your heads down right now. Heads down right now. If you're watching the video, I trust that you're going to do it now, Ada. If you're watching the video, I trust you are also closing your eyes and not looking at the screen anymore, because that would be a sin, because I've asked you to do something. Okay, open your eyes. What happened? Yeah, okay, actually, that's good. That's exactly what I wanted you to say. How do you know? No, Linda has blood dripping off of her fangs. How do you know that the bloodthirsty Linda had moved? How do you know that moved? That's the clue. No, that is not how. That's not how in real life. How do you know? Oh, no. No. Come on, Isaiah. Yeah, okay, there you go. So motion is a change in position. There we go. Motion is change in position. My point is that you don't have to see something in the process of moving to know that it moved, because motion is defined as a change in position. And you know this instinctively. You also know probably instinctively that marker drawings don't actually move. But the magic trick is that your brain, when something is in a different spot, even if you didn't see it, assumes movement. And so the motion is a change in position. So if something changes its position, it has moved. What is a position, by the way? You know this. Yeah, place it's at. Yep. Place it's at. Let's just do end it with the sense with a preposition, like a like a potato. Yeah. Okay. So motion is a change in position. Now the question, that was the 8th grade science trick, although I did make it a little bit better for 9th graders. But the question to make this good for physical science, for people who measure things and do math with things, is that how do we measure that? How is linear motion measured? How is it measured? So in order to measure linear motion, we need to know two things. You tell me. I mean, for one, I already gave this example, and you already said something today. Let's have someone else join in the discussion. Thank you, though, Isaiah. Although some of you are far too active in the discussion, you're saying nonsense. But someone besides Isaiah say some good stuff in the discussion. I'm sorry, what did you say? I can't imagine it's right.
It's not right.
What did you say? Nonsense. Oh, he just said the word nonsense. Okay, I couldn't understand because he was mumbling. What do we need to measure motion? Okay, I will start from there. He says how many feet, we call that measurement distance. So there are different units that we can use to measure distance, but we need to know how far. What else do we need to know?
How
Yeah, how, okay, let's say that one, how fast. And when you say how long, you could be talking about length, which is another version of distance, but I don't think you are. I think you're talking about how long it took, which we would call what other thing? Time. And let's put a line through how fast. Speed. There we go. And in fact, these things are related. We could know one other thing that is important. Is it, it's very easy to use this example because it's just right there. If you look out the window, as I can't help but do as I'm doing these videos, if you look at that Jeep drive by, is it important how far it has gone, how fast it is going there, and how long it takes? Yeah, there's another very important thing for the driver. Okay, almost, because direction is exactly it. There's another very important component for that driver, because it's not just about, unless you're in a race, it's not just about how fast you're going. It's about that you're going to a specific place, you're going to a specific position, and so you need to be going the correct direction. And so with all of these things combined, we call that velocity. Velocity, which is v with a little line over it, is equal to distance traveled divided by time. So v with a line over is velocity. Does anyone have any knowledge? I can't remember if I told you this last year, but does anyone know at all why we would put a line over this? It's a special kind of quantity that means it has direction. Do you remember what that's called? Put it over here. I'll get a little arrow to it. It's called a vector quantity. A vector quantity is one that has both magnitude. You guys are so funny. So funny. Yeah, really culturally appropriate. That movie came out in 2008. A vector quantity is one that has both magnitude, that is how big it is, and direction. So if you can remember that with your dumb little quip from a 17-year-old movie, then that's fine. If that's a good way for you to memorize, that's fine. But magnitude, one thing you might not know, even if you memorize it by that child's speech, is magnitude means greatness. Magnitude means how big something is. And so distance has magnitude. How far away something is, how distant it is it has a magnitude. Speed has a magnitude, faster or slower. Time has a magnitude, longer or shorter amounts of time. But direction does not. And so direction is the other component of a vector quantity. Vector quantities have magnitude, how big they are, and a direction. So v with a line over is velocity. By the way, when we type things, we usually put vector quantities in boldface, and scalar quantities, that is quantities that only have, I'm going to point an arrow to this. Speed is a scalar quantity, S-C-A-L-A-R. Speed is a scalar quantity, which means it only has direction, or sorry, only has magnitude. Only magnitude. Whereas vector quantity has also direction. When we're typing things, scalar quantities are written in italics, and vector quantities are written in bold, but your handwriting, not. So there's some exceptions. There's some green zone of handwriting in the middle here, but most people's handwriting, mine included, you're not going to be able to tell if it's italic or bold, and so we usually just put a line over. In any handwriting, we put a line over vector quantity. So v is velocity. We'll talk in a second about what units that's measured in. D is distance, and lowercase t is always time. Little side note, what is capital T, do you think, when we use that as quantities in an equation? Yep, there you go. Lowercase t is time, capital T is temperature. In the SI, how do we measure time? What's the base unit of time in the SI? Seconds. What's the base unit of distance in the SI? Meters. So if we have an equation that tells us distance divided by time, distance in meters divided by time in seconds, what's the unit for velocity in the SI? Meters per second. Now, can other units be used to measure speed and velocity? Yeah, of course. Any distance unit divided by any time unit will be a speed unit. And if that also has direction, it will then be a velocity unit. So if we have, I'm going to give you an example of a unit and you tell me what we might measure with that. If I say feet per second, what is something we might measure in feet per second? You know, some of you probably know. What's the customary, there's something that we customarily measure in feet per second. Muzzle velocity of a firearm or a paintball gun or something. That's we measure that in feet per second. So if you're into guns, we measure that at least in America, we measure that in feet per second. What about if I was talking about something being done in centimeters per year? What might that be? A snail. That's actually the customary thing we use to measure the movement of plate tectonics, of tectonic plates, if you remember what those are. Yeah, snail's example. But you're getting into the right thing. Is that if we use small units and long periods of time, that's something moving slow. What if I was talking about something being measured in kilometers per second? I mean, by the way, we could measure anything in any of these units. It's just to keep the numbers at a manageable level. Something measured in kilometers per second might be like a jet or a rocket ship. Yeah. Good. So this is velocity. You'll remember from last year that there are various ways that velocity can change. One, what do we call a change in velocity? Change in velocity. Someone said it. Raise your hand. I heard the right answer. Avery. Acceleration. There are 3 ways an object can accelerate. 3 ways it is accelerating, yes, and 2 ways it is not accelerating, no. What are the 3 ways it is accelerating? What are the 3 ways it is changing in velocity? Well, you tell me. What are 3 ways it could accelerate? What are 3 ways its velocity could change? No, come on. Any object. Talk about it in terms of... Okay, there we go. Let's start with that one. If it changes direction, right? I'm glad you came up with that one first. Change in direction. Change in direction.
Hey, sorry to interrupt. Is Trey coming to the cross-country meet?
I think he might. Okay, besides change in direction, how else can things change their velocity? What's another word for change in velocity? Yep, so accelerate is what we're talking about. Change in velocity is acceleration, but I think I know what you're getting at, Natasha. If we, in the common way that, especially I said in my 8th grade science video, police officers or truck drivers, when they say accelerate, they mean go faster, right? Speed up. And there's another word that sometimes police officers or truck drivers, or really any layperson might use when they mean slow down, which is the last one, which is decelerate. But that word does not exist in physical science. And acceleration is any change in velocity and includes all 3 of these. You will never see the word deceleration on any of your physical science materials because to the scientist, they're all changes in velocity, which is acceleration, which is the general term for a change in velocity. People in society, people who are just walking around doing stuff might use different terms, accelerate and decelerate for these 2, but that doesn't really have any bearing in science. Don't forget change in direction. Something can be going the same speed, but turning, and it's still accelerating. What about, how then is it not accelerating? If an object is not changing its velocity. Okay, at rest is the easy one. What's the other one? There's another one. Okay, I love that word. Maintain speed. So constant speed in a single direction. You can feel acceleration. Your body feels acceleration. Have you ever had your eyes closed, maybe sleeping in a car? You can tell when your mom's going around a corner. Have you ever been trapped in the trunk of a car? You can tell when the car turns, even though you can't see anything, right? You're not watching the world change. You trapped in the trunk of a car. You can feel that someone's going around a corner because that's an acceleration. Your body feels acceleration. Could you feel them speed up? Yep. Could you feel it slow down? Yep. Now, you wouldn't be able to, if it was a very comfortable ride in the trunk of the car, you wouldn't be able to tell the difference between if you're just sitting in a parking lot or if you're maintaining speed at cruise control on the highway. Now, in real life, obviously, engine noise, tire noise, that kind of stuff, you really would. But your acceleration sense would not detect the similar speed. If there was nothing else going on, single speed in a straight line, that is not acceleration, and so it would be indistinguishable from rest. Acceleration is calculated. This is important for us in science. Acceleration, another vector quantity, equals change in, which is the Greek letter capital delta, velocity over time. So delta means change in. It is the shape of a triangle. That is called the Greek letter delta. I'm going to just point a little arrow at that and call it delta. And that means change in. Have you seen the word delta before anywhere? I can think of 3 ways you might have seen it. Yep, okay, there's an airplane brand named Delta, and its logo, guess what, is a triangle, and it's actually a triangle made of triangles. I have never heard of that, so I guess there are 4. There's a river delta, which is how a river goes into the ocean, and it's kind of a triangle shape. And then, okay, 5. And then the other one I was thinking of is there's a brand of faucet called Delta, and you sometimes see it on the drain, and that brand has the little triangle for its logo. Anyway, Delta is a triangle, and it means change in. So if I have Delta V, that's change in velocity. If I have Delta F, that's change in force. Delta T, change in time. It's just whatever follows it. This just means change in whatever variable comes next. So A is acceleration. We'll talk about what it's measured in a second. V, again, is velocity. What do we measure velocity in? Yeah, you should know because we just talked about meters per second or meters divided by second, meters over second. And then T is, again, time measured in what unit? Seconds. So if our equation is meters per second on top divided by seconds on bottom, what's our acceleration measured in? Meters per second, or we sometimes call it meters per second squared. Those are the standard acceleration units, and so that's how we measure acceleration. That's how fast motion is changing. It's not always meters per second. It can be any speed unit over a time unit. So miles per hour per second. That's the usual way that acceleration is measured in America is miles per hour per second. How long did it take for that speed to change? So maybe 60 miles per hour. 0 to 60 is a common way to talk about the acceleration of racing cars. 0 to 60 in 4.6 seconds. Well, that's a change in velocity, 0 to 60, so 60 miles per hour per, whatever I just said, 3.6 seconds, right? That's how we measure acceleration. A speed unit divided by a time unit. And last thing, what causes this acceleration? I'm moving left, I guess. We're doing this in Hebrew. We're moving right to left. What causes acceleration? You can do it down. I don't care how you write your notes. What causes acceleration? Cause of acceleration. You should remember this from last year. Anytime an object's motion is changing, that's an acceleration, it's caused by a unbalanced force. Unbalanced force. Why did he specify correctly, by the way, unbalanced? Yeah, if it's balanced, there is no acceleration. Are there forces acting on you? You're relatively still, at least in the frame of reference of planet Earth, which if you are confused about how frame of reference works, go back and watch 8th grade science video from this year or from your 8th grade science video, but I'm assuming you already know about how we talk about that motion is relative. But in the frame of reference of planet Earth, you're sitting still. Are there forces acting on you? Yes. Tell me two of them. Really, gravity's pulling you down. How come, if gravity's pulling you down, how come you're not accelerating down? Because the force of gravity is balanced by the ground holding up the chair, holding up your bottom, right? That's called the normal force. And so you, you're not Linda. This is you, though, sitting in a chair. Nice. Gravity is pulling you down. Gravity definitely does exist. F sub g pulling you down, but that is balanced by F sub n, the normal force of the chair pushing you up. Sorry, you have your hands in the air because it's chicken nugget day. There you go. These forces are balanced. So let's go down the chain. These forces are balanced. So will you accelerate? No. Will you change your motion? No. And so one of these must be true. You are either at rest or maintaining speed. Are you at rest? Well, here's what's interesting, is that in the frame of reference of planet Earth, you are at rest. But in the frame of reference of some other things, you are maintaining your speed. And so your frame of reference, you are not accelerating. And that, well, I guess I was going to say that acceleration does not have a direction, which, because there is no acceleration, it doesn't. So because there are no unbalanced forces acting on you, you're not accelerating, you have no change in velocity. When you go to get up in 3 minutes, what's going to happen? When you hoist yourself out of your chair, what's going to happen? Yeah, you're going to be putting another force into this diagram, which will cause an acceleration, which is a change in velocity, and your speed will go from at rest, 0, to whatever your speed is. Do you have questions about this? I need to print off